I love our conversations about math, but I really want to be entertained today, even dazzled. I want to see something that's almost magical.
Funny because I like being entertained and I like magic, but I really want more math today. So clearly we have a problem.
I think we have the perfect solution because today's guest is a magician and a mathematician. He's a two-time Greater Atlanta Magician of the Year and a professor at Georgia Tech.
Wait, so he can fool me and outsmart me?
Not just you, but both of us. And that's exactly why we're talking with Matt Baker about math and magic and their connections and how they're related and why maybe magic secretly runs on math.
So I'm Autumn FNAF.
And I'm Noah John Siracusa.
Join us in today's episode where you get to learn about math and magic.
So, Matt, we just heard you're a mathematician and a magician, and I just want to start by finding out how does your math enrich your magic?
Yeah, interesting story there, I guess. So I use math to improve some magic tricks or come up with new principles in magic. So for example, I think there'll be a link in the show notes to the episode I did on Penn and Teller's Fool Us. And that was in part based on a math principle that I had read about, but I kind of jazzed it up in various ways and turned it into something new that fools even magicians that knew, the original principle. So that's one way that math enhances the magic that I do. But I think also being a mathematician is really good for training in creativity, in the process of working on a hard problem. Because in some ways, designing your own magic tricks, which I like to do, is not so different from math research. You have a problem you want to solve. And sometimes it's really hard because in magic, you're basically trying to do something that is impossible, right? So, which math research feels like that too sometimes. And you just have to keep pushing against boundaries, right? You have like some mental blocks, some technical obstacle that is stopping you from accomplishing what you want. And you just have to try to get through the walls from different angles, try different strategies. And I think the discipline of being a mathematician is very helpful with that. And finally, I would say that being a math teacher, which I've been doing for over 25 years, is really helpful for performance, just in terms of being comfortable in front of an audience, in terms of knowing how to explain things, because I also lecture to magicians on my original tricks. And that's something that, I think I can do better than the average magician, just because I've spent over 2 decades teaching students.
Now, in that case, let's reverse it. If you take your original magic tricks, do they tend to be mathematical?
A lot of them do, but some of them don't. So I don't have a firm rule about these things. Like, I want to do really good magic. I want to entertain audiences. I want to do things that are amazing. If math can help with that, then that's like a secret weapon that I can use. But there are many other techniques. I mean, magic, one of the reasons it's so interesting is that it involves many different things, right? It's psychology, it's science in terms of like, magnetism and all kinds of, other principles. Or nowadays, you can use your phone to do magic tricks with various technology. And there's also just the performance aspect of it, telling a good story. There's obviously like sleight of hand manipulation, and I like all these things. So to the extent that math can help add on to all of that, I think it's great. But if I come up with a good idea or what I think is a good idea for a magic effect and it has nothing to do with math, that's fine too. Sometimes I use math just in the presentation. The method has nothing to do with mathematics, but I frame it in some way as like referencing my own interest in math or my being a mathematician. And that's just a tool I can use to relate to the audience, because it's always good, to have a unique personality when you're a performer and to have people know who you are. And people find it interesting. I guess that's why you asked me on the podcast, that I mix these two different things. And so I like to highlight that rather than hide it, when I'm performing.
So let's zoom in a bit on that performance side and even, I would say, aesthetics. So in math, I think it's kind of easy to think math is just proving a bunch of statements, figuring out what's true. But we know that it's more than that. It's really finding theorems that are surprising and remarkable and beautiful. There's some aesthetic thing that is very hard to pin down, but it's really what drives us. And I imagine
Yes.
in magic, there might be something similar where a trick might, you might technically define a trick to be anything that fools an audience, but I'm sure some are more entertaining than others. So, do you find an aesthetic similarity in what drives your math and in what drives your magic?
That's a great question. And yeah, I think your characterization of things is spot on. And yes, I think there is a relationship there. I would say that my interest in math, which I think we'll talk about more later, my particular interests and the things that I've done tend to be probably more focused, more aesthetic based than a lot of mathematicians. I'm less interested in proving a really hard technical theorem if no one will find it interesting or unusual or captivating. There's a lot of that to go around. And just find it hard to get inspired by that. And yeah, similarly in magic, right? There's many things that I see that fool me. I mean, the more you know about magic, the harder it is to get fooled. So a lot of stuff these days that I see doesn't fool me, but I can still get fooled by things, but often I don't care, right? It's just, even if it's like a math trick, it might even be based on an interesting principle. But if it's not entertaining or doesn't have a hook to it, yeah, I mean, so what? Like, it's not that hard to fool people. What's hard is to get them to really care and invest in it and really be hanging on the outcome of a trick and then to be really surprised. And that's what creates something memorable. That's what creates a really impactful feeling. And ideally in math research, that's the case as well, that, something is just genuinely surprising, changes the way you think about the way stuff works. And I mean, that's sort of the ultimate goal. And yeah, so it's hard to find such things. It doesn't happen every day.
Does it help you with public engagement more?
I'm sure it does. Yeah, like I think that I'm somewhat more successful than um, a lot of my peers in math at the public engagement part. Also, maybe at maybe not public engagement, but engaging, say, undergraduates in research or even high school students. And I think part of that is just because I'm drawn to problems and methods, which don't rely as much on technicalities, but more on some kind of aesthetic or creative aspect that in favorable situations can be more broadly accessible. So in that way, I just follow I think Noah put it well. I mean, I just follow my aesthetic kind of gut feelings sometimes more than any real precise technical program. And I just trust that if my gut tells me something is interesting or has potential, that I spend time on it.
So we've talked a lot about the synergy between your math and your magic, but let's be real for a second. You have a family, you're a top-notch mathematician, you're award-winning magician. There's only so many hours in the day. How do you find that there's sometimes intention where you just are never fully invested in one because of the other? And if so, how do you deal with that?
Yeah, of course, that's a challenge. I'm not sure I should be one giving advice to people on this, right? Because I feel like I'm not very good at this, but I suppose I've built strategies to deal with it that might be interesting or helpful for some
Well,
people.
we might be interested in hearing some of them.
Because
Yeah.
it's different hearing it from a man than it is from a woman.
And
I will say that.
everyone
Now,
has
my
different
wife thinks
perspectives.
I'm terrible at time management, and she's probably right. But to me, I guess I would say that everything comes down to having a sense of purpose and knowing what you're trying to do and having a rough ordering of your priorities. Now, these get in tension with each other quite often, and sometimes it's not clear how to resolve those tensions. And sometimes I think I spend time on things that would have been better spent elsewhere. We all do that. But
No, not us. We've never done that, but
right.
interesting
No,
to hear.
no, no, not at all.
But let me say that I guess at some level I do have a sense of priorities that help guide me. So first of all, I do put my family first, or I try to, when it comes to big things, right? So I think, Noah, at least as you know, a while ago, I got offered a tenured job at UC Berkeley, which is a real top math department. It was kind of my dream job. And I took it for a year, but I couldn't make it work with my family situation. And so I left after 1 year, went back to Georgia Tech, where I am. Georgia Tech's, of course, also a great university. So it's not a big, huge sacrifice in some sense. But I mean, Berkeley's a special place for mathematics. And but it was just clear to me that I had to put my family first. And so, that wasn't a really hard decision at the end of the day because I had those priorities straight. In terms of math and magic, I prioritize math as the thing that pays my bills. And of course, my teaching, it's sort of non-negotiable that I'll do a certain level of competent job in my teaching. I could always put more time into being prepared than I do. And sometimes the students notice that I've been not spending enough time thinking about that day's lecture. But I prioritize that to some extent. And then my research, when I'm really inspired by an idea that I think is going to be impactful in some way, then I spend a lot of time on it and I'll prioritize it over basically everything until I get it out of my system that I either know it's going to work or not. And that can be frustrating for the family sometimes, right? When you go off and I'll stay up real late and then, I usually get up at 6 a.m. So then I'm like cranky the next day. And, I do the same thing sometimes with magic where I have an idea and I'll stay up late or I'll prioritize that. But what I try to do is structure things so that like magic, I basically do on the weekends. Math I do on weekdays, and like family in theory is the evenings and then part of those weekends. Of course, these things all bleed into each other in unpredictable ways all the time. But I just have a sense of like, okay, this thing is important either for my career, but nowadays I'm like pretty well set in my career. I have tenure and I'm not like super worried about my reputation in terms of like whatever,
Let
improving
me
it.
try asking a more pointed, provocative version of the same
Yeah,
question.
sure.
Do you think you would be a better mathematician had you never gotten into magic, or do you think you're a better mathematician having gotten into it?
That's a great question. I don't know the answer for sure. I do know that I need another outlet for my energy and creativity. It's not sufficient for me to focus on math all the time. I've been like that since I was a little kid. I've always had many interests in music, in theater, in reading and writing, uh, sports, and so it's just not an option for me to kind of like think about math 24/7. My brain, yeah, just gets atrophied by that. So I need some outlet, like whether magic is the perfect one, I don't know. It's the one I've found that keeps me maximally kind of engaged most of the time. But yeah, I think it has improved my math in some ways that are hard to make completely tangible. But I would contend that, yeah, probably overall it's improved my skills as a mathematician just because it helps me think outside the box a bit more.
Now, if you're being a magician, what helps people understand human thinking that you would have never noticed before if you're switching from one topic to the next?
Well, I don't know if this is answering your exact question, but in magic, like in mathematics, clarity is extremely important. Right. So clarity of effect is paramount in magic. People think it's like distraction, misdirection. People think of that sort of thing in magic. But you have to be very careful because if I want you to watch something, I mean, there's no magic unless you can compare the initial conditions to to the ending conditions, right? Magic happens in between those two. And the initial conditions have to be completely clear to you so that you appreciate that something impossible has happened in between. If I say, look, there's a pigeon over there, and you turn your head and then you turn back and something's different, that's not magic, right? I must have done something. You lost the clarity of the effect. Or if I give instructions that are very complicated, I say, all right, take the top card and put it in the middle, and now give it 3 cuts, and now do, and like you've kind of forgotten what we've done, and you don't know if the deck was shuffled at the beginning or not, and you're not sure whether your card is lost, or then there's no effect. So in that way, you learn how to communicate very clearly with people, how to get them to remember what you want them to remember from an effect. Okay, the deck was shuffled. It was definitely lost in the deck. There was no way he could have known, what I was thinking of. And then poof, something impossible happened. And so I do think, coming back to math again, right, that when you're writing and communicating math, this is also extremely important. You have to understand what people are thinking in order to know how to structure things in a clear way. So you have to know what your audience, whether it be your students or your readers of a math article or your audience in a magic show, you have to know what they're thinking in order to be able to guide them where you want their mind to go. And so I think that is largely human psychology, but, also just clarity in the purest sense.
Well, I think it's great to talk about magic, but I can think of one thing that's even better. You can imagine what this is. Autumn, what do you think? Is it time?
I think it's time. Maybe you should do a trick for us, Matt.
Okay, well, I came up with something that involves a little bit of math and can be done both for our audio and video audiences. So Noah, do you have a calculator?
I happen to have one, yes.
Okay.
Look at that.
So if you could pull that up, I am going to try to read your mind using mathematics. Okay. So we're going to create a random number that I
7.
couldn't possibly know. So I want you to type in a digit 1 through 9 on your calculator.
1 through
And then-
9.
And then hit
Okay.
times.
Times, all right.
Now type in a different digit and hit times again.
So still 1 through 9?
We're just going to keep hitting single digits and multiplying them together until you get a really big number, like maybe 8, 9 digits.
All right, I know. Just keep doing this?
Going. Yeah, just keep
one at a time?
multiplying random kind of digits together, one at a time.
8 or 9, repeating or not.
1, 2, 3.
Yeah, you can repeat the same digit. It's fine. Just don't hit, like 1 times 1 times 1 or something.
All right, I
like
think I
that.
have 1,
It'll
2,
be
3,
really
4,
dumb.
5, 6,
And
7.
don't keep hitting
right.
the same.
I just multiplied 8 digits together, or I'm about to.
Okay, so how you have like an 8-digit number or so?
No, I typed 8 individual digits.
I'll type a few more.
Type a few more? All right.
It's best if we have like a 8-digit number, say.
All right, I'm going to press equals and see what happens. All right.
Yeah, you got something?
Yeah, 8 digits.
Great. Perfect.
Magic. It worked.
Now, Noah, there's obviously no way I could know what number you have in front of you or really
That's
anything
correct.
about it at all. You're far away. But let's try something. I want you to mentally circle one of the digits in front of you.
Okay.
All right. Now, don't circle a 0 because that can be confusing, but any other digit mentally.
All right.
Okay. And now I want you to read off all the other digits except the one you circled in whatever order you like. Now, if there's like several of one digit, read all but the one, the occurrence that you circled. Does that
And
make
should
sense?
I purposely shuffle the order? It doesn't matter.
It's totally up to you.
All right, I'll
For
start-
everyone's benefit here, just do it nice and loud and slow.
All right. 0, 0, 5, 0, 9, 8, 8.
Okay, look at me, Noah. Think about the digit that you circled in your.
Yes.
It was a 6, wasn't it?
Ridiculous. How did you? That's. See, here's what I don't like about magic. It's supposed to be exciting. That is infuriating. How did you do that? I'll be honest, that blew my mind. I have no idea how these things work. And I know magicians are not supposed to reveal their tricks, but you're not a magician, you're a mathematician. And that was kind of a math trick. So are you willing to give us a little insight into that?
There are many different names for it. Yeah, I can share this one. Everyone who's listening should raise their right hand right now and swear that they will only share the method with someone else if it's for the purpose of teaching math concepts, which is why I'm sharing this now.
It's a deal. We'll also put it on YouTube, but beyond that, we'll keep
Yeah.
it secret.
No, but I think it serves a good pedagogical purpose, and so I'm happy to share. Normally, we keep these things secret.
We appreciate that.
So here's how this works. And it's cool because many people watching or listening will be able to go do this immediately to their friends and family. So let me explain how this works somewhat quickly, but hopefully you'll all get the idea. So there's two parts to this trick. And I think that's what makes it really interesting in fooling is there's like two principles at work and they sort of cancel each other out. Okay. So the first one is that there is a small probability that this trick doesn't work. I mean, if the volunteer does follows the instructions exactly and I don't make any mistakes myself, then I calculated that it works like over 90% of the time. Okay, so it's quite reliable, but maybe not the thing you do on live TV if it's your one shot at stardom. But I like taking chances in magic. If the worst thing that happens is it doesn't work, and then you just kind of admit that it's
Wait, can I just pause? Because I didn't know that this is a thing. So are there a number of magic tricks that only have a certain fixed probability of being successful that people perform?
There are a number of such things. Yeah, it's not everything, of course, but yeah, a lot of the greatest magicians in the world, the ones I really look up to, they take a lot of chances. And then when they get a hit, it's a huge, impact because, it seems completely impossible. So I think there's really value in that. Now, it's normally good to have a backup plan, right? So one of the things magicians will do is take a chance, but if the best possible hit doesn't work out, they still have a way to finish the trick in a entertaining and mystifying way. They're going
Sort of
for
hedging their risk.
Yeah, it is really like a hedging strategy in some way. So that's one of the things I like about this trick is that people assume things are like algorithmic in some way or just there's a fixed process. This one is not quite like that. What I'm counting on is that you will end up with a number that is a multiple of 9. Okay? And it's very probable because if you ever type the digit 9, by definition, you'll end up with a multiple of 9. But also if you ever type 2 3s or 2 6s or a 3 and a 6 in any order, you'll end up with a multiple of 9. So when I say this has a 90% plus chance of working, it depends how long the number you end up with is, how many times you multiply it and how randomly you did it. But yeah, in practice, with the instructions I gave, it should work like almost all the time. Okay. So now, unbeknownst to anyone but the magician, I know something about your number. I know it's a multiple of 9. At least that's the working assumption now, right? And so now we use this old technique called casting out nines, which says that number's a multiple of 9 if and only if the sum of its digits is a multiple of 9. And this is used, as some of our listeners and viewers may know, in like check digits, in error correcting codes and various things. It's a very old principle. And, it's used to catch accounting errors and things like this. But in this case, we're using it for a magic trick. So the idea is if I keep track of the sum of the digits that you read out loud, the one that's missing is the one that when I add that digit to my mental total will give me a multiple of 9. And so all I did was, as you read the numbers out, I kept a running total in my head. And I said, what do I have to add to that to get a multiple of 9? And that's it. But I think putting those two principles together, nobody knows that this has anything to do with multiples of 9, right? So it's not like they're not really clued on to that. And you're not leading them to any particular multiple of 9. You're letting chance govern things. So I like that trick a lot. And
That's
nowadays,
amazing.
anybody can do this anywhere because people have calculators on them all the time because of smartphones.
And I think there's going back to Autumn's question about psychology, if you had started by saying, pick a long random number and make sure it's divisible by 9, it would feel like a math problem. It wouldn't feel magical. So the fact that you did have to take a slight gamble, even though it, introduced that probability of failure, that really to me is what made it feel like magic. You just said a number. So my brain wasn't heading towards properties like casting out nines. If you just mentioned the word nine at any point, I would have felt like, all right, I kind of have a sense of what he's doing mathematically. So that's really interesting that you had to push into that risk zone just to get us psychologically liberated from thinking mathematically.
Yes. And this is, I mean, I don't know who invented the coupling of these principles, but a lot of people who do this, some version of this trick, do it in a more deterministic way. They'll say like, all right, start with the number whatever and then multiply it, and they just start with some multiple of 9 and they tell you what to type. They seed it for you. And then, yeah, but I don't like that. I just think it kind of, will give it away, certainly to mathematicians, but it also just doesn't feel as free. And so this is something I also like to use in card magic where, I want things to just feel totally free. And so sometimes you have to take chances in that way where, yeah, you could do it in a more structured way that would guarantee that I know what your card is and where it is and that I can find it. But it's much more interesting if somehow I take a little chance that convinces you that there's no way, but still gives me a good shot at succeeding.
Now, this makes me think a lot more about mathematical intuition. Is mathematical intuition more like pattern recognition to you, whether it's in magic or in your research, like storytelling?
Well, I think all these things are important. I don't know how I would rank them, in terms of relative importance, but intuition and pattern recognition is really important for me in math research. It's probably the basis of almost all the breakthroughs that I've had is just the ability to like look at analogies between things, think about patterns. That's just how I think, and how a lot of mathematicians who want to be creative will think. So that's huge. Also, storytelling, in my opinion, is underrated in the math world, in academia, right? I think, and that's something I've learned as a magic performer and studying magic. It's also underappreciated in magic. People relate to stories. I mean, that's why you all are doing this podcast with real people, right? Stories are incredibly important. It's how our brains are really wired to think. Data is great. We all love data. It's good to use data in making decisions. It's good. But, at the end of the day, what moves people, what often makes people decide to do something or not is not data, but a feeling of connection, a feeling of being part of a storyline. And so I think this is really important in math in that, I try to structure my papers a bit like stories when possible. I think I spend longer on the introductions than most mathematicians do, just trying to explain what the narrative is here, right? What is the history of this problem? Why is this interesting? Where does this lead? What does it connect to? If that's not clear, then I feel like the whole paper is, a bit pointless because nobody's going to read the technical details unless they have a sense of what the narrative arc is here that makes this interesting. And then same with a magic trick. If I don't hook you at the beginning and have some story that's being told, something idea that's being communicated, it's not interesting. In the trick I just performed, it's kind of minimalistic. I start out by saying, I'm going to use math to read your mind. And I just go into the trick. But I think that's enough. You just need a short hook, right? I mean, it's something interesting. So now you want to see what's happening here. And then I'm like, just type in random numbers. And that's kind of interesting too, because you're like, where's this going? I mean, nothing's happened yet. There's nothing he could know. So I'm building a story there. So I think it's really important.
So in your research, one thing I find really interesting is you tend not to just stay in one territory. it's hard to even pin down what part of math you're in. You kind of hop around and build these bridges, as you said, through analogy, as Autumn mentioned, through pattern recognition. I was going to ask you about one specific one, but I decided, let me just ask you instead, can you think of your favorite piece of mathematics that you've worked on and just give us like a little 2-minute tour of it?
I do have many favorites, and I move around
Nope,
a
you only
lot.
get one.
Yeah, it makes it hard. But I'll
It's
choose
like
one.
kids. You have to have one.
Oh, I have to choose a favorite kid after this? Wow. This is a tough interview. Uh, yeah, so I think my most influential paper, certainly in terms of number of citations, as well as the one that was probably the most unexpected development, was the Riemann-Roch theorem for graphs. And so a brief story of that is the following. There's a theorem in algebraic geometry called the Riemann-Roch theorem. I'm not going to try to explain it on a podcast for general people, but it's a really important result that goes back to the late 19th century, with Riemann was a great German mathematician of the late 19th century. So
Very
this is
roughly, it's about counting sections of a line bundle, if you know those words.
right. Yeah.
If
Which
not, don't worry.
means things to many.
I didn't know that, okay?
There we go.
I wasn't going to ask.
We just like it because it's a cool name, Riemann-Roch.
Yeah. And okay, so I learned about this theorem in graduate school, and we used it a lot in various classes I took. Then I was using it in my own research. So it was like embedded in me. But then I was thinking about, okay, so Riemann-Roch's about things called Riemann surfaces, which again, you can imagine like a donut with 3 holes in it. That is like a typical Riemann surface. And so I was thinking about analogs of those, 3-hole donuts in this world called p-adic geometry, which again, I'm not going to try to explain briefly on an audio podcast, but it's one of the things I was researching for a long time that my advisor, Robert Coleman, was known for. And I realized there was like an analogy between these worlds, p-adic geometry and complex geometry or Riemann surfaces, that I hadn't seen explored before, that, seemed to be a really interesting analogy to me. And at the heart of these p-adic Riemann surfaces are graphs, like nodes connected by edges, like the thing that, information networks, thing that a lot of people have probably seen graphs or networks in various contexts. So just like a normal finite discrete graph, in some ways is analogous to a Riemann surface, which in theory is a much more complicated object. And so I started thinking about this analogy, and it occurred to me that there might be a Riemann-Roch theorem for graphs. And I started playing around with it. And I guess what's interesting about the story from maybe this podcast point of view is the following.
And let me just pause to say, Riemann-Roch, it's a very geometric thing. Graphs are very combinatorial. So the fact that a geometric theorem would have anything to say about networks, a very combinatorial thing, it's really shocking.
Yeah, it's unexpected. And actually told a mathematician friend about this idea. And he said to me, well, I don't think you should spend a lot of time on that, because if that was true, it would have been done already. So this is very bad advice, I think. I'm glad I didn't follow it. But it's a very tempting way to think. And I'm sure I've fallen prey to that many times before, many mathematicians, right? Where we actually don't pursue what could be a important idea because it's easy to think that like everything worth doing has been done already. But of course, you're not going to get too far as an academic mathematician if you always think that way. So you have to balance out like being humble and being kind of honest with yourself about and then the possibility of like, okay, not everything interesting has been done.
I'm just thinking, imagine if OpenAI, someone said, chatbots, someone's already done that. That's not going to be worth any money.
Yeah, you can't think that way, but you do have to think that way sometimes because, you can't get carried away and think, I'm going to prove Fermat's last theorem, and then, I get sent lots of false proofs all the time by people that, who think that this idea has never occurred to anyone before when it's always like the same kind of basic mistake or something. But anyway, I digress. So to come back to Riemann-Roch for graphs, here's the other interesting thing about the story, I think. So I had this idea. I ignored my colleagues' advice to stop thinking about it. I decided to put an undergraduate REU student on the task one summer. I just wanted him to write some sort of simulations to see if what I was seeing in my hand calculations could be kind of replicated on a larger scale, so we could get some evidence that there really is something here. The problem was the original way I was thinking about this by analogy with Riemann surfaces was a little bit technical. It involved something called the Laplacian matrix of a graph. And then I think the exact formulation that I had in mind was not easily communicated to an undergraduate in a way that made a lot of sense. So I had an idea for translating the problem I had in mind, which was like a linear algebra problem about matrices attached to a graph, into a game. So I came up with a game played on a graph where you put some number of dollars on each node, and then you move dollars around the graph according to simple rules. Like each vertex can donate $1 to each of its neighbors or borrow $1 from each of its neighbors, but you can't only give to some of your neighbors, you have to give to all of that. And you're allowed to repeat this any number of times, and the goal is to get everyone out of debt, right? So to have all the vertices, all the nodes having non-negative amount of dollars. And the question is, when can you do this? What is like a sufficient condition, or if you're really optimistic, necessary and sufficient condition for this to be possible?
This seems like a metaphor for capitals. Can we spread money so that everybody is benefiting?
No, and in fact, it turned out that this game had already been played around with by other mathematicians. So I didn't know that there was this whole thing called chip firing. Norman Biggs, who actually had a position at London School of Economics, had invented this kind of dollar game on a graph. But his rules were like very slightly different from mine, and it kind of makes a technical difference. So my exact version of the game was a little different from what people had considered, because Biggs was actually considering the situation where one vertex is like the bank and is allowed to go into debt as much as they want. And I was sort of allowing everybody to go into debt, but hopefully only temporarily. So anyway, slightly different. But basically, this had already been studied. And the theorem we ended up proving with my undergraduate student, or at least seeing was should be correct, turned out had already been done in a different form by other mathematicians. And even physicists had studied chip firing, which again, at the time I didn't know. But I just came up with this as a way to explain what I was doing to a student. But then that intuition coming from thinking of this as a game turned out to be extremely helpful, not just for me in coming up with this Riemann-Roch theorem, along with my colleague Sergei Norin, but also for subsequent researchers who have built on the theory that we created here. And I think the fact that it's such a easily explained, easily understood game makes it appealing for people, and also provides like psychological tools for, because we have some intuition about how to play games.
And that's really amazing to think that here you have number theory, geometry, physics, economics, and basically at the same time, you're discovering that they all involve the same game. And that's kind of this bridge between them that I think is, as you said, very unexpected and really quite beautiful.
Yeah, so it was a very, I can say to say it modestly, it was a very lucky thing, because all these subjects that are interrelated and this beautiful analogy that had gone undiscovered, I kind of stumbled upon. I also managed to team up with a, gold medal winning IMO mathematician in Sergei Norin, who was able to actually prove the conjectures I had come up with. But at another level, I appreciate that it's not all luck, right? I mean, luck is, as they say, the residue of design. So I was well prepared to take advantage of that luck, because I was willing to spend time on a bit of a crazy, out there, somewhat outside the box idea, just because I had this, as I was saying before, a kind of intuitive feeling that there could be something there. And if there was something there, it would probably be very interesting and maybe even important.
And as you're discovering this amazing hidden bridge and these connections, and as you said, what might be your greatest research to date in your career, what emotion would you say you were most feeling as this was unfolding?
Many different emotions. I think they all cycled through, right? So part of it was just like should I just give up on this? Why am I spending time? I could be doing something a little more obviously with a payoff, because it did take quite a bit of experimentation to kind of realize I was onto something here. So part of it was just like self-criticism, but part of it was genuine excitement. Like, this really looks like it could be a thing. And yeah, why, if this was a thing, why didn't anybody else look at this? So then I would spend time on the internet just doing Google searches, like trying to find, oh, this must have been done. What's going on here? Right. So a lot of sort of doubt mixed with confidence that I should trust my intuition. And then, yeah, when we finally proved a theorem, I mean, so, and the way that happened, my undergraduate student gave a talk on his summer REU work. Sergey Norin, who I didn't know at the time, was a postdoc at Georgia Tech. He attended the student's talk. He got interested in it because it was so easily explained in terms of a game. And he went down, my student stated a conjecture at the end of his talk, and Sergey went home and thought about it over the weekend, and Monday morning knocked on my office and introduced himself and said, I think I can prove your conjecture. Now, that wasn't the full Riemann-Roch theorem. It was just a part of it. But then I said, okay, let me tell you what the real conjecture is now. And, in another week, we had that. And then I was really excited because I just had a sense that this was going to be big, but I actually I think it's become more influential than I would have expected. Sort of hundreds of citations now, and there have been entire conferences organized around this kind of like chip firing and connections to geometry. And I don't think I was so confident in the idea that I would have expected that. If I had, I probably would have submitted it to a better journal.
I'm curious, with how technology is changing from proving things with your work, do you see AI coming into effect at all? Where do you see this
Yeah.
with modeling, with it could even be with your magic tricks? Where do you see AI and technology aiding and speeding up mathematics even as a whole?
Yeah, so this is something I've been thinking a lot about lately, as have many mathematicians and magicians. And I use AI quite a bit now, just in the last year. It has really gone from something that was like mildly useful to something extremely useful. I'm not into making predictions about, in magic I am, but not about the future of technology, right? Like, I think it's moving so fast that I have no idea what the timeline is. But for sure, in the pretty near future, AI is going to take over large swaths of math if it hasn't already. I don't think mathematicians will be obsolete in a matter of years, but I do think that we are going to have to change what we do and how we do it and what we focus on. And I think it's both terrifying and exciting. Terrifying in the sense that it could mean sort of the end of math as we know it in academia. And, that's terrifying because I think it's a beautiful thing that's been around for thousands of years. And to think that we could be on the cusp of sort of making this classical, beautiful subject kind of quasi-irrelevant is difficult to think about. But on the other hand, I think there's lots of reasons to be optimistic. At the moment, I think we're in a wonderful time where AI is just a super helpful assistant. Like, I still have ideas that AI is not going to come up with right now, maybe no time soon. I don't know. But, I can still come up with ideas for seeing patterns, seeing connections between different parts of math, ideas that I would have been too scared or intimidated to work on before. And now I'm actually exploring some of these things because I have this new tool, right? This like technically amazing tool that can, as of when we're talking today in February 2026, it's able to prove like lots of ChatGPT can prove technical lemmas that it would take me weeks or months to prove. And I'd probably get distracted and never just like, work through all the technical hurdles. It can do it in 5 minutes. And this is like quite astonishing. So it means that some of these crazy ideas that I have, most of which end up being nonsense, I can actually explore. And I have a pretty recent example of this in my own research. We don't have time to probably talk about all the details of it, but I came up with something recently related to mathematical biology and phylogenetics motivated by algebraic geometry, which still working out all the details of, but I'm quite confident, and I'm working with an undergraduate student on this and quite confident now that it works. I mean, he coded this up and the algorithm I came up with works and might even be faster than a lot of the existing, if not all the existing algorithms. And I came up with the idea myself, but AI was really helpful in just like testing out the idea, whereas like with that Riemann-Roch thing, it took me months of hand computations and I almost gave up. Here, I was convinced within a day that I was onto something, because ChatGPT can just really solidify a lot of these things that were tenuous in my mind. And it helped me write some preliminary code to do some stuff because I'm not a very good coder. So it's phenomenal. It also helps in magic because I write scripts now using ChatGPT for my tricks, right? So I'll like take the rough idea of what the trick is and kind of what I want to communicate, like what that key hook is. But then like AI will help write a script that has jokes in it and has more structure, which again, I used to spend months on these scripts. And now like sometimes I can, in 1 hour or less, I can knock out a pretty polished script. So I think it's amazing and it's like a assistant at the moment. But yeah, at some point it might just be better at all these things than all of us. And then it will feel a bit paralyzing, I suppose. But we're not there yet and hopefully won't be there anytime in the extremely near future. So I find it incredibly exciting.
And I think we always want to see a magician live in person, and hopefully we'll still want to see mathematicians live and in person, or at least
Yes,
written.
Yeah.
absolutely. Now, is there anything that you wanted to add that we haven't covered?
Well, I mean, just on the AI thing, I would say I'm organizing a workshop on algebraic geometry and machine learning at Carnegie Mellon this summer. Yeah, so this is through ICARM, which is a new institute called the Institute for Computer Automated Reasoning and Mathematics, and I'm very excited about what that institute is doing. And so I wanted to kind of be a part of some of the initial activities of the institute.
Is there any one piece of advice that you would want to give to an aspiring mathematician who has a serious side interest in magic, just like yourself?
Yeah, maybe I can broaden it to just say aspiring mathematician with a side interest in anything that is, like music or art or writing, anything that might have a tie-in with math, but it's basically a separate thing. And I would say that, my advice is that we have to follow our passions and trust our own intuition. It's very easy in academia to feel like you have to do what the people in power think you should be doing, right? You get a lot of guidelines as a young assistant professor in mathematics of how you should be spending your time and, don't spend too much time on this, don't focus on your research, blah, blah, blah. And yes, I mean, you should focus on your research. If you don't produce good research, you're not going to succeed in academia, but that doesn't mean you have to do it to the exclusion of other things. And it doesn't mean you have to work on only the things that the community currently considers important. I think it's really important to have at least some part of your time devoted to just doing things you're passionate about. And if it's playing guitar or drawing cartoons, or doing magic tricks, I think it's important to do that. And especially if you feel that you need that creative outlet in order to stay sane, in order to stay happy, and maybe in order to stay creative. And so I think it's important to cultivate that, but just realize that managing time is hard the more interests you have. And so it doesn't make things easier necessarily, but some people need that. And so I think if someone has the feeling that they need to do this, they can look at me as an example of someone who managed to to keep it up. I will say in grad school and as an assistant professor without tenure, I wasn't doing magic for about 10 plus years because I felt like I couldn't take the time to devote to it. But I picked it up again. And maybe in retrospect, I wish I hadn't stopped at all. But in any case, it's never too late to pick things up again. And so you can also bite the bullet and really focus for a few years on research stuff and getting tenure and all that nonsense. And then later on, you can relax a little bit and say, like, what I really love, where I think I have my biggest impact and get my greatest joy is in combining these things and rekindle that. And that's sort of what I did. And my math career certainly hasn't obviously suffered from picking magic back up as a hobby. So I encourage people to believe in themselves, believe in their own intuition.
Math is about numbers and shape, formulas and equations, lemmas and theorems. But when we communicate math to others, there's an element of performance. Mathematicians don't just convey facts, they entertain audiences with knowledge. They instill a sense of wonder, and they leave audiences a little bit spellbound. The best mathematicians are magicians. Maybe call it a math magician. And in Matt Baker's case, this is literally true. So thank you, Matt, for sharing your talents and insights with us. And as always, stay curious and stay informed of the world around you.